Welcome to the last video lecture for chapter 17. In this video we'll be looking at beats and we'll also be reviewing standing waves. This follows along in section 17.4 all the way through 17.6 in your textbook. So beats, Mr. Wolf can't beatbox, he's hip, he knows the moves. But anyways, beats occur when two sounds are produced at a very similar frequency. These two sounds interfere with each other and they create what is called a beat frequency. The beat frequency is a frequency, it's the sounds become louder or quieter, and you kind of hear this little womp 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 or something else like that. You obviously are thinking about rap music right now, but it occurs when the two sounds are very close in frequency, and the beat frequency itself is actually the difference between the two sound frequencies. So it's when they interfere with each other. So here's a drawing that shows two different frequencies. Let's say that the dashed lines each represent 1 second, so those dashed vertical lines. The top frequency would be 2.5 hertz or 2.5 hertz. The middle, the middle blue one or the bottom blue one would have a frequency of 3 hertz. The difference between the two of them is half a hertz, or saying that it would complete 1 cycle in 2 seconds. So if you kind of see this beat frequency on the bottom of when how they're interfering with each other and creating this loud and soft or faint interference, it occurs like it takes 1 full cycle occurs in 2 seconds, based on the idea that each dash line is 1 second. So a beat frequency is the difference between two similar frequencies. They're going to be a little bit different, and it creates that little, there's a loud part, there's a quiet part. We'll look at this a little bit more on a graph of how it looks like in school, so in class tomorrow. But it's just the difference, one frequency minus the other frequency, gives you the beat frequency. Standing waves, as we've seen, are waves that reflect back on themselves and cause constructive and deconstructive interference within a confined space. They kind of fit, so to say, or it just happens due to their wavelength and frequency that they fit and interfere with each other within this confined space. The area where the wave itself is at a maximum amplitude or moving back and forth the most is called an antinode. The point where the wave doesn't seem to move at all, those points are called nodes. So we've already seen this a little bit before here, but the node is where the waves don't vibrate, and the antinode is where the wave has maximum vibration. All objects have what's called a natural frequency or a fundamental frequency. This is also referred to as the first harmonic. And the second, third, etc. harmonics occur based on a multiple of the first harmonic. So if the first harmonic is 10, the second harmonic is 20 hertz, etc., going up from there. Different objects can have resonate or have this building of a wave occur when at different frequencies, if they're driven at one of those natural frequencies. This is when a disturbance occurs over and over again at the correct frequency to cause it to increase in amplitude, increase for the vibration to increase in amplitude. You see this with, you can kind of hear if you take a speaker and you go through different range of frequencies, you hear different things within a room or something like that start to vibrate and move back and forth. So that's kind of the idea there with resonance. But the idea of fundamental frequency and harmonics is that each harmonic is a successive jump up in frequencies based on the fundamental of that first harmonic where you have that oscillation or that resonance occur. It really comes from where the standing wave occurs on a string.
So here's what's happening. A plate is just vibrating due to a sound produced, and as you can hear the sound changing, the frequency, the pitch is also changing along here with this sound. And what they're doing is they're adding sand on this plate here, and they're going to change the frequencies. And you can see as it goes from the fundamental all the way up through fourth, fifth, sixth, etc., all the way up to higher level harmonics here, and the different frequencies and the patterns that it creates on this plate. The area where you actually see the sand, those are going to be the nodes because it's not vibrating. So that's going to be destructive interference at those points, and the constructive interference occurs at where there is no sand actually. Hopefully you can hear this because my ears hurt now, and I'm just going to turn the sound. Well, I guess I'll just plug my ears. This is pretty wild. That one was awesome. Love it. So this is just from YouTube here, so you can hop on there and go and look at some other ones if you want to find some.
When we look at longitudinal standing waves, we look at this within some tube. So the tube can either have be open at both ends or open only at one end. If the tube is open at both ends, then the oscillation within that tube length is some harmonic of a half wavelength. This is because there is a antinode at the top and an antinode at the bottom, and going to be of each open for the open side. So this is for an open tube. There is an antinode at both ends, and it's at a half wavelength for each one of those. So for the fundamental frequency, it would be half the wavelength for the length of the tube in order for there to be resonance. And this, in turn, with musical instruments, creates the different notes that we hear, the different pitches that are allowed that you get by pushing your fingers over different buttons, etc., to open, or different openings to allow the air to escape. For a tube that's closed at one end, you have an antinode at the open side and a node at the other end. And this here is in a quarter of the length of the tube. This is a quarter of a wavelength. So this means that for the fundamental frequency, the length of the tube is 1/4 of whatever the wavelength is. And then as you go up, the frequency goes, it skips the even numbers and goes up to 1, 3, etc., and goes on from there. So once again, this has applications in musical instruments, which allow you to create different pitches of sound as you go through. Three quick questions here just to review this video. First, how do you calculate the beat frequency for given two different frequencies? Second, what causes a standing wave to occur? And third, the point on a standing wave of the maximum displacement for the vibration is called the blank. Please fill these in online. Thank you very much, and have a good night.